Back in 2002, three brilliant physicists, Dyson, Kleben, and Susskind, published a paper that's one of my all-time favorites. They took a few ideas about our universe that most physicists agree on and followed them to a conclusion so bizarre they actually called it a disturbing crisis. So let's dive into this cosmic puzzle and see exactly what they found. Right, so we're pretty sure our universe is expanding. And not only that, the expansion is speeding up. It seems like it's just going to keep going forever, pushed along by something we call a cosmological constant, or dark energy. Now, on the surface, that sounds kind of cool, right? An infinite future? But if you really take that idea seriously and follow the logic, you end up in a very weird place. So what on earth is so disturbing about a universe that expands forever? The best way to get this is to treat it like a detective story. We're just going to follow the clues, one logical step at a time, exactly like they did in the paper. And when we get to the end, we'll see exactly why they were so unsettled. Our investigation starts, funnily enough, not out in the vastness of space, but with something way, way simpler. To get our heads around the entire universe, we're first going to shrink things down and just imagine a simple, sealed box filled with gas. Trust me, this little thought experiment, it's the key to understanding the whole thing. Okay, before we go any further, we have to talk about one crucial concept, entropy. All it is, really, is a measure of disorder. So if all the gas molecules in our box are tucked neatly into one corner, that's a very ordered, low entropy state. But if they're all spread out, buzzing around randomly, that's a disordered, high entropy state. And the one big rule, the second law of thermodynamics, says that things in a closed system always go from order to disorder. So picture the life cycle of our box. We start with that perfect low entropy state, all the gas in the corner. Then, whoosh, it spreads out, filling the entire box. Entropy increases. Eventually, it settles into a state of maximum disorder, or heat death, where basically nothing interesting is happening. But, and this is the absolute kicker, if you wait long enough, an almost infinitely long time, by pure random chance, all of those molecules will just happen to find themselves back in that original corner. Now, this isn't some kind of magic. It's a real thing in physics called a Poincaré recurrence. It's a statistical guarantee that any closed system will eventually, randomly, fluctuate back to a low entropy state. It's wildly improbable at any given moment, of course, but given forever, improbable things are guaranteed to happen. So what does a simple box of gas have to do with our universe? Well, that's where things get wild. Okay, now for the giant leap. What if our entire universe behaves just like that box of gas? It sounds like a crazy idea, but there are some really powerful theoretical reasons to think it might. So because the universe's expansion is accelerating, there's a horizon out there. Light from galaxies beyond that point will never, ever reach us. It's a point of no return. This bubble of space that we can see and interact with is called our causal patch. And for all practical purposes, that patch is our universe. It's our own personal, finite cosmic box. Now, the central assumption of the paper is a deep idea from string theory called horizon complementarity. You don't need to know the details, but the takeaway is simple. It says that our causal patch can be treated as a totally closed, isolated quantum system. It has a finite amount of stuff in it. It can't get any more disordered than a certain maximum entropy. In other words, it really, truly is just like that box of gas. And this is a super important point. In some other theoretical models, you can imagine an outside observer poking the system, throwing some energy in to reset it. But in our accelerating universe, our causal patch has no outside we can talk to. Nothing can get in from beyond the horizon. So if our universe is going to get out of its high entropy heat death, it can't be reset from the outside. It has to be an inside job. It has to come from a spontaneous, random internal fluctuation, just like our box of gas. Okay, so let's connect the dots. If our universe is a finite, closed box, and if the only way to create new ordered states is through internal fluctuations, I think you can probably see where this is headed. The conclusion is pretty much unavoidable. Our universe must experience these Poincaré recurrences. It has to fluctuate. And that means our universe isn't a one-and-done deal. It's part of an eternal cycle. It fluctuates out of a state of total disorder, lives out its cosmic history, dies, and then waits for the next fluctuation, over and over and over again. So just how big a fluctuation are we talking about here? Well, our standard model of the Big Bang, inflation, says the universe began in an incredibly ordered, super low entropy state. The paper estimates that entropy at about 10 to the power of 10. Now that sounds like a big number, but cosmically, that's incredibly tiny. It's a state of extreme order. But the final heat-death state of our universe, its maximum entropy, that number is, well, it's almost incomprehensibly huge. It's 10 to the power of 120. So to get our universe started, you need a random fluctuation that can bridge that insane gap from almost total disorder all the way back to pristine order. So what this model is saying is that our Big Bang wasn't some unique singular event. It was just an exceptionally rare but statistically guaranteed fluctuation, an unbelievably lucky roll of the cosmic dice that's bound to happen again and again over unimaginable timescales. But it's right here that the story takes its truly dark and disturbing turn. The physicists actually named this final twist the misanthropic universe because it leads to a paradox that kind of seems to devalue, well, everything we think we know. Okay, let's ask a simple statistical question. If you're relying on a random fluctuation to create a universe with observers like us in it, what's the most probable, the most statistically cheap way for that to happen? Is it to create a perfectly low entropy Big Bang and then wait 13.8 billion years for it to evolve? Or is there a shortcut? And here is the absolutely terrifying answer. The paper argues that it is statistically overwhelmingly more probable for a universe just like ours to just pop into existence instantly, complete with stars, planets, and even observers with false memories of a past that never happened, than it is for a genuine low-entropy Big Bang to occur. Why? Because the instantaneous universe is a much smaller, and therefore much more likely, deviation from a state of total chaos. Just let that sink in. The implication is staggering. If this model is correct, then it is far, far more likely that you, me, our planet, and all our memories of history just fluctuated into existence 5 seconds ago than it is that we're the product of 13.8 billion years of actual cosmic evolution. Our entire history is a statistical illusion. And the authors themselves put it plainly. They say that while these instant creations seem miraculous, statistically, there are just so many more ways for them to happen that they would vastly dominate any universes that were created through a real history, like the one we think we have. So we followed the logic and arrived at a paradox where our entire history is probably fake. That's not great. How do we escape this? Well, the authors are very clear. This isn't just some philosophical game. This disturbing conclusion is the direct result of combining 3 cornerstone ideas in modern physics. 1, that the cosmological constant is real and permanent. 2, that our universe is a closed holographic system. And 3, that quantum mechanics is the ultimate rulebook and information is never truly lost. So to get out of this misanthropic paradox, you have to throw out one of these assumptions. But which one do you pick? These are all incredibly successful fundamental ideas. Do you give up on dark energy? Do you throw out holography, which has taught us so much about black holes? Or do you try to rewrite the rules of quantum mechanics itself? It's a heck of a choice. The paper ends by offering its own preferred escape route. Maybe the simplest answer is that the first assumption is wrong. Perhaps the dark energy we see isn't a permanent fixture of reality. Maybe it's something that will fade away, preventing our universe from ever becoming that eternal finite box in the first place. And that final thought leaves us questioning the very nature of our cosmos and its ultimate fate.